Numerical integration. Some functions do not have antiderivatives that are elementary functions, or simply the antiderivatives cannot be found. So the fundamental theorem of calculus cannot be applied. Consequently, rather than evaluate definite integrals of these functions directly, we resort to various techniques of numerical integration to approximate their values. Three such techniques are described in this video. Thanks in advance for watching this video. If you like this video, don't forget to like and subscribe to the channel and activate the bell. It is very important for the continuity of this channel. Let us start by remembering that an integral is equivalent to a summation operation. We defined the definite integral of a function over an interval as the limit of Riemann sums. The summation corresponds to the sum of the areas of rectangles, approximating the area between the graph of f of x and the x-axis over the interval. The midpoint approximation for estimating a definite integral uses a Riemann sum with subintervals of equal width, delta x, and the midpoints of each subinterval. In other words, the midpoint approximation is the sum of the areas of the rectangles of height f of c sub I and delta x as the base, where c sub I is the midpoint of each subinterval. We can state the midpoint approximation as follows. The midpoint rule. Let f of x be defined on a closed interval from a to b that is subdivided into n subintervals of equal length delta x. Then the interval can be approximated by We can also approximate the value of a definite integral by using trapezoids rather than rectangles. Look at the figure. Each subinterval forms a trapezoid whose height is the width of each subinterval given by delta x, and the bases are the values of the function from x equals a to x equals b. We see that the first trapezoid has a height delta x, and the parallel bases are the values of the function at x sub 0 and x sub 1. The area of a trapezoid is 1/2 the height, here it's the width, times the sum of the length of the bases. Thus, the area of the first trapezoid can be given as follows. We find the total area by adding up the areas of all trapezoids. Factoring out the delta x over 2 and combining the pairs of overlapping terms everywhere, for x equals a and x equals b, we obtain the following approximation. The trapezoidal rule. Let f of x be defined on a closed interval from a to b that subdivided into n subintervals of equal length delta x. Then the integral can be approximated by the next two examples will make the theory clearer. First, we use the midpoint rule with n equals 5. That is, we divide the interval from 0 to 1 into 5 subintervals of width delta x. The midpoint rule gives we now use the trapezoidal rule. Pay attention. With the midpoint rule, we estimated areas of regions under curves by using rectangles. In a sense, we approximated the curve with piecewise constant functions, that is, the midpoints. One way to view the trapezoidal approximation of a definite integral is to say that on each subinterval we approximated the curve by using piecewise linear functions, that is, straight lines. Another rule for approximate integration results from using parabolas instead of straight line segments to approximate a curve. This approximation technique is referred to as Simpson's rule. Simpson's rule is based on the fact that given any 3 points, you can find the equation of a quadratic through those points. In order to gain some insight into Simpson's rule, we will evaluate an integral of a polynomial of degree 2 on the interval from a to b. The difference between two cubes and the difference of two squares can be factored in as follows. By expansion and collection of terms, the expression inside the brackets becomes. So we can write Consider the graph of the function f of x. The red line represents the graph of the function. To develop Simpson's rule for approximating a definite integral, we again divide the interval into n subintervals of equal width. This time, however, n is required to be even, and the subintervals are grouped in pairs. Then, on each consecutive pair of intervals, we approximate the curve by a parabola, as shown in the figure, through the blue lines. Each parabola passes through 3 consecutive points, as shown in the figure. We now using a polynomial of degree 2 as an approximation of f of x on each subinterval, passing through 3 points. We will find the area under the first parabola. We will now repeat the process for the next 2 parabolas. We will add the results to get the total area on the interval from a to b. Observe that the coefficients in Simpson's rule have the following pattern. Repeating the procedure on the entire interval from a to b as n tends to infinity produces the following theorem. The Simpson's rule. Let f of x be defined on a closed interval from a to b that is subdivided into n subintervals. N is even, of equal length delta x. Then the integral can be approximated by. Let's solve the same example, but now we will use Simpson's rule with n equals 4. We divide the interval from 0 to 1 into 4 subintervals of length 1/4. We now apply Simpson's rule. In many applications of calculus, we need to evaluate an integral even if no explicit formula is known for y as a function of x. A function may be given graphically or as a table of values of collected data. The next example, you will see how to use Simpson's rule to find an approximate value for the integral of y with respect to x. I will solve the next example in detail, step by step. Pay attention.